A very warm welcome to all of you. Myself Rajan Choudhary, Professor in the Department of Civil Engineering, Indian Institute of Technology, Guwahati, instructor for the NPTEL MOOC course Pavement Construction and Technology, funded by Ministry of Education, Government of India. Today's lecture will be the lecture 6 under the module 3, which will deal with the which will be having the discussion over the characterization of materials which are used in pavement subgrade construction. At the very beginning, I would like to acknowledge the use of text, informations, graphs and images sourced from various textbooks, codal standards, journal articles, reports, newsletters and public domain searches. As per MORTS 2013, the different materials which falls under the category for use in the subgrade pavement subgrade construction includes it says that the MORTS says that the materials permitted for use in, it states for embankments also normally wherever any filling is required to raise the level of the ground, then we go for the first the embankment construction, thereafter the subgrade construction. So for both the cases it mentions that the materials which are permitted for use in embankment subgrades, and when you are constructing the earthen shoulders also aside your paved shoulders, and miscellaneous backfills, especially when some retaining structures are constructed, there you go for the backfill material also. So what type of materials MORTS recommends for use under these different categories, which are your embankment, subgrade, earthen shoulders and miscellaneous backfills, include soil, muram, gravel, reclaimed pavement material which is extracted from existing pavement material, which can be derived from whatever you can mill it, get it from, or the scrap already existing from the any pavement construction material. Fly ash, industrial waste, pond ash, a combination of these can also be used. Reclaimed material, when you are trying to reuse it with some modification, or a combination of fly ash can be there along with your natural soil. So this are the materials which are recommended for use. And finally, all these materials have to be, this is very important, by default they cannot be used. This combination or the selection of material has to be approved by the engineer in charge. Now what soil states for? What the term, this is a big term, soil encompasses different kind of materials. So sediments or other unconsolidated accumulations of solid particles produced by the physical and chemical disintegration of rocks which may or may not contain organic matter. So this is a big umbrella under which different kind of materials will come into picture. So soil is a general classification term which is used for materials which are used for your subgrade or embankment construction. Another terms which is quite popular when we say that it is a clay soil. Now again a type of soil, but which falls under the category of clay soil. What is that one? Clay soil, an aggregate of microscopic and submicroscopic particles. Particles are very fine. When the particles are even finer than 2 microns, so then that comes out to be your say 0.002 mm. So this is less than 2 microns. So in this particular case, if the particles are even finer than this particular one, they normally falls under the category of clay. It's an aggregate of microscopic and submicroscopic particles derived from the chemical decomposition and disintegration of rock constituents. These particles normally exhibit a plastic nature. We will discuss what a plastic nature is and how that particular one is determined. Now all these aspects will be related to pavement engineering, especially transportation engineering. Normally the people working in the soil engineering, they go into very in depth of these soil characteristics, but here we will focus more which are quite relevant to our pavement construction or road construction aspects. So they say that the clay size is normally one which is finer than your 2 micron. The other category we normally refer as silty soil. This is another type of classification of a soil is there. Silty soils are there. These are fine grained soils or fine grained portion of soil Again, these all are under the bigger umbrella of the soil. So, which exhibits little or no plasticity and has no strength when air dried. So, normally clay soils, they have high plastic nature, silty soils normally non-plastic, and then you might have heard about terms sandy soils are there. So, there are certain regions in when sandy soils are there. Then you might have heard the term black cotton soils are there. So, these are the different type of nature of soils which can be classified through different means. Those things we will discuss here. So, when it comes to the three more important is, one is the general soil classification and the common classification which say that the soil may be clay in nature or it may be a silty soil. So, when it comes to the sizes, it says that the portion of soil which is usually finer than 75 micron. So, 0.075 mm, which is lesser than this particular one, and coarser than 0.002 mm, that is your 2 micron, because normally the one below 2 micron comes under the category of your clay soil. Now, what test we normally do to understand the behavior of a soil so as to judge the suitability of that material for your road construction, especially because we require a bulk quantity of soil for embankment and subgrade construction along with the construction of your earthen shoulders or protection of your edges, side slopes, but the major quantity will be required for your raising the level in terms of the embankment and the subgrade. If there are some major fills are required, because if you are constructing some roads in low lying areas, then again the quantity required may be very high. So, there are some quite popular test procedures which are followed for characterizing or evaluating any soil for its use in road construction. Soil intended to be used in embankment and subgrade is primarily evaluated, characterized in the following means. How it is done? One is you work out the soil size distribution. So, we just now discussed that okay, if the sizes are less than 2 micron, it becomes it is like a clay soil. If the ranges are from 2 micron to 75 micron, it is a silty soil. So, on the basis of grain size distribution, you can work out the to a certain extent the nature of the soil. Then comes the another important limits you might have read in your other courses related to soil engineering: liquid limit, plastic limit, and the third is plasticity index. So, these are three terms and the three characteristics which we normally determine for a soil to judge its suitability for using subgrade and embankment construction. Another is your free soil index. Then we work out the characteristics in terms of its compaction, density. So, two parameters there it is determined is optimum moisture content. Along with it, there is, when we work out the optimum moisture content, it is corresponding to your maximum dry density. So, optimum moisture content or maximum dry density are worked out also. Now, in addition to this, for the strength purposes, we normally go for California bearing ratio. We will discuss about it, and normally this test is done under soaked and unsoaked condition depending upon the conditions in the field under which the road will be constructed. And another parameter which is used is unconfined compressive strength or resilient modulus. So, these are some of the common evaluation practices which are used for judging the suitability of any soil for use in road construction. Now, as I mentioned, what is your gradation or soil size distribution? So, I can pick up the sieves which are where the material is expected to lie. So, if a material is having sizes say ranging from 10 mm or say 20, even more than that 10 mm, I can say for 20 mm. If the sizes are from 20 mm and going below say 1 micron, even lesser than 1 micron. So, I try to do sieve analysis accordingly, but for me practically working out with these sieves is possible, the gradation is possible up to a certain sieve sizes only. Below those finer sieve sizes, it is not possible to do using these different sieves. So we will look into it. So the particle size distribution of soil quantitatively expresses the proportions of mass of various size particles present in the soil. So I just want to see how much of the material is retained over 75 micron. So all this which is getting retained over the above sieves forms a part of the one which will be retained over 75 micron. So I may be interested to know how much percentage is passing 75 micron sieve. That will give me how much my soil is finer than 75 micron. So how much chances are there that it is towards the silty nature, and then I may even look to know how much sizes are finer than 2 micron. But doing this gradation with sieves are usually possible for sizes above 50 micron. For sizes lower than 50 or 75 micron, we normally do not go with these individual sieve sizes. We have to go with either the pipette method or we have to go with the hydrometer method. So grain size distribution, and what I get, I'll show you in the next slide what I get out of this sieve, this gradation analysis. I'll get the distribution curves, and through these distribution curves I can get an idea about the nature of the material, and I can work out where it can be suitable. For coarser materials I can even see whether that materials can be used as a drainage layer, filter layer, separation layer. So all these characteristics can be on the basis of my this gradation I can work out. Two methods are given for finding the distribution of grain sizes larger than 75 micron, because this is mainly what is possible conveniently with these different kinds of sieves. The first is wet sieving, and which can be and the second is dry sieving. Now the when do we go for wet sieving and dry sieving? Normally when clay content is more, the clay is getting adhered to your bigger sizes of particles. So in that particular case you will prefer that when clay content is higher, you will prefer for wet sieving, so that all those clay which is adhered or attached to your bigger aggregate particles or bigger soil particles gets washed, and you get a good determination of the sizes on different sieves. So then you will prefer to go wet sieving, but it takes more time, and if there is lesser quantity of clay, you can comfortably go with the dry sieving also. And as I mentioned, for sizes less than this particular one, you normally go with the pipette method or the hydrometer. Now we have many good equipments available, particle size analyzers, which can give you sizes which can go nanometers up to the sizes of nanometers also. Now I will just give you an example. What do we do under this gradation analysis or sieve size distribution? So I am randomly picking up. So I say if I take these 4 sieves, so there is one sieve which is 100 mm and another is 75 mm, 19 mm, 4.75. So what I will do, I will take a standard material and I will put that standard material on the top sieve, and it will be shaked. Now there are, you have laboratory sieve shakers also, and sieve sizes are of different sizes are also. You can have 15 centimeter dia sieves, you can have 30 centimeter dia sieves. All those different sizes of sieves are available depending upon what is the range of particle which is available is present in your soil. So if I do this with this particular, if I am finding that there may be coarser particles, 70 mm particles or 75 mm particles are also present in my soil, then I will prefer to keep these sieve sizes from 100 mm, so that whatever is there above 75 mm also gets rid. So I have taken a standard material and I have sieved them, I have stacked them, keeping the coarser one on the top and the finer one at the bottom. So now this particular one, so I have sieved it, I found that no material is present retained on my top sieve. Now there is an important consideration, depending upon the sieve size, there is a requirement how much maximum material it can sieve. So that is to be taken care. So it says the maximum weight of material retained on each sieve at the completion of sieving should not exceed the prescribed value corresponding to the sieve size given. So this is an important thing. If you take more than that material, the sieving will not be correct. So, the appropriate amount of material that can be retained over particular sieve is to be taken into consideration while you are doing this dry or wet sieving. Now, here I have seen no material is retained over this particular sieve. On this sieve 710 grams of material is retained, here 1030 is retained, here 2195 gram is retained, and below this particular one I can go up to 75 micron. This is an example, I will go up to those particular sizes, and on the bottom at the end I will put a pen. So, below 75 micron, if I am going up to 75 micron or 50 micron, at the bottom of it I will have my pen. So, whatever passing through 4.75 mm sieve is getting retained over. So, this is my total material which have been retained over it. Now, the total weight of this material forms to be 4195 grams, and initially I may have taken say 4200 grams. Then you may say, where is this 5 gram gone? During this sieving, some fines may be lost. You will prefer to do a controlled sieving, so that this fine as less as possible, these fines are lost for your sieving. Now, so but still chances are there that some discrepancy will be there, especially in the total quantity of material you have taken, and finally what comes on the individual sieve size. So, what for my consideration I will take what all present on the different sieves. Now, with the respect of this 4195, I can work out how much percentage retained is there. So, 0% is 0 divided by total material will be 0%, 7110 divided by 4195 give me 16.92 percentage. So, this gives me percentage retained on these individual sieves. Now, I want to know how much material will get retained over this 19 mm sieve. So, I need to work out the cumulative percentage retained. So, for this particular one, on the 100 mm no material is retained 0%, on this 75 16.92. So, when it comes on 19, this will be 16.92 plus 24.55, so that will be your 41.47. When it comes to 4.75, this 41.47 plus 52.32 will be the one. So, if I put all the material directly over 4.75, that means 93.79% will get retained and remaining will pass, and then definitely at the pen it should be 100%. So, one is in terms of cumulative percentage retained, second we talks in terms of the cumulative percentage passing. So, 0%. So, this means exactly you have to subtract the cumulative percentage passing through 100. So, if 0% cumulative retained, so that means all material passed. So, 100 minus 0 is your cumulative 100% passing. When it is 16.92 cumulative percentage retained, my cumulative percentage passing will be 100 minus 6.92. So, that will be, so if I put all the material, 83% of my material is passing through 75 mm sieve. Or 58. So, this gives me idea. Then I would like to see say 75 micron. See how much material is passing, 80% material is passing. I can see okay this. So, a very large share of the material is there, which may be in the portion of either silty soil, or if more finer in the lower sieves, it may be under clay in that case. Now, once I have this particular one, I can plot this gradation. This cumulative percentage passing I can plot, usually plotted on a semi-log curve, where this is your the sieve sizes are plotted on a logarithmic scale, and this is your normal arithmetic scale. Now, here you can see the percentage passing is vary from 0 to 100%, and these are your sieve sizes. So, here you can see this is 1 micron, this is 10 micron, this is or this is 0.1 mm, this is 1 mm, 10 mm, 100 mm up to. Now, here what important thing you can see, when I plotted different, I did this gradation on different samples, maybe soil or many these this gradation has to be done, or the sieve size distribution, whether it is soil or any granular material, in the same fashion. It only thing which will vary will be the sieve sizes which you will be using for granular materials, and the one which you are going to use for when you are looking for soils, because the particle sizes which are present will vary in different material. Now, you can arrive various informations through this size distribution curves. Now, this is one size distribution curve, you can see. So, this is, you can see there is a range of material present between these sieve sizes also, range of material which is present between these sieve sizes also. So, I can see if this is 1 mm and this is 10 mm. So, what is there? This is 40%, 1 mm, you can see this is 40% is passing for 1 mm. I can work out for this particular one, and how much for this is for, sorry, this is for 10 mm, and for 1 mm I can see around 15% passing. So, in between this 1 and 10 mm, so from 15 to 40, so around 25% material is. So, I can, from this I can work out from 1 to 10 mm I have materials in the range of around 25%. When I write on this particular one, writing normally does not get good. So, 1 to 10 mm 25%. So, you will see different sieve sizes, you have good amount of materials, or a good distribution is there. This good distribution means you have a well graded material where all sizes are present. So, normally this kind of distribution comes under a well graded material, and depending I can see how much material is finer in that case. So, if I am having a 75 micron one, I'll see 0.075 maybe here. So, in this case I can see here 5% material is passing, here only 2.5% is material. So, I can look into the fineness of the material also. And now, here you can see there is one gradation curve, the another gradation curve which is here is in this particular one, in this ranges, or specifically if I go for a wider one, here this is the one, and I can prefer, so this may be 0.1 or 2, so 1, so it may be 0.15, around 0.15 may be somewhere here. So, 150 micron will be there, and this is, you will have, say, I can say this is my 2 mm. So, in this particular range you have a very small percentage, even less than 5% material is there. So, there is one particular size which is missing here. So, this kind of curve show that there is a gap graded, some particular sizes are missing up. Now, the other one shows is this kind of one, where you can see all my percentages are within a very small range. So, here it is 100% passing, and here you can see for this particular curve, here when it comes it is 10% passing. So, within this narrow range of C, all my material is available. So, this becomes a uniform graded soil. So, this is, you will say, a uniform graded soil, and along with it, on the basis of sizes, I can say it is a silty soil, or it is a sandy soil, or it is a clay soil. So, this gradation curves gives me idea whether it is a well graded, it is a uniform graded, it is a gap graded, it is a well graded one. Now, the other important aspects comes in terms of the Atterberg limits. Now, under this Atterberg limits, we want to determine especially the nature of the soil, how it behaves in the presence of water. So, the Atterberg in 1911 proposed a series of empirical tests to determine the consistency and plastic properties of especially fine soils. Now, three important things which we require especially for determination for our purposes here are: one is liquid limit, second plastic limit, and on the basis of these two we get the plasticity index. These are three, and another the limit which can be extracted out of it is shrinkage limit. Now, if I add, you can see if a soil sample is there with you, if you add water to it, you keep on adding, there may be a certain consistency. Consistency means amount of water at which the soil sample along with water may start flowing. So, and the if the water level is reduced, you might have felt that when you are moving on a ground, if there is a presence of water, then chances are there it's slippery is there, your leg gets stuck into the soil. So this why? Because the behavior of the soil changes with the presence of water or the amount of water which is present. Now the one term which is used is the liquid limit. It says is the water content expressed as a percentage of the weight of the oven dry sample at the boundary between liquid and plastic states, and it says it is the water content at which the soil starts flowing. So if this is my water content, this is my moisture content, water content with respect to a dry weight of a soil. So if I keep on adding, after this particular one, the soil mass will start flowing with more water to be added. Now there is another limit which is normally considered is a plastic limit, and what it says is the water content expressed as a percentage of the weight of oven dry at the boundary between the plastic and semi-solid states. So this is the consistency. If I keep on reducing it below this particular one, the soil will be, you will not be able to remold the soil sample or it will crumble. So if I reduce the water content below this particular one, it normally comes into a semi-solid state. So this becomes my, I'll from the way in which these are determined, you will get a more clear picture. And if I further reduce the water content, so here the maximum water content at liquid limit when it starts flowing, if I am reducing it below this, when it comes, it starts behaving as a semi-solid, and if I keep on reducing, the soil volume will not keep on changing. So this is the one which we call as the shrinkage limit. It says is the maximum water content expressed as a percentage at which any further reduction in water content will not cause any change in the volume of the solid mass. So there you can see how the behavior of the soil will change with the change in the water content. Now the first one, more things will be discussed here, especially in the determination part. How do I determine liquid limit at the laboratory scale? There are various methods of doing this particular one. The most commonly one is the mechanical method, which is in terms which looks like here. So in this case, and the other one is one point method and a cone method. Now here what is done, for any soil sample for which you want to determine the liquid limit, you take a standard mass of the soil, and this is all done as per the IS 2720 part 5, where this the complete description of the determination of the liquid limit is given. I will give you a brief idea. So we take a soil mass, we add water to it, and here this soil will be filled in this particular apparatus, and here and specifically the sizes which are less than 425 micron are taken, and a groove is cut here. Now in that, after that particular one, you are going to give these this compaction levels to this particular one, and this is a handle, you can see this particular one. So it will raise this cup and will allow it to fall down. So every rotation will raise it and allow it to fall down. Now this particular one, so what you are going to do, if you want to note down the water level at which these or the number of blows at which these two soil samples after cutting of these grooves comes closer. So if number of blows, or I can say the drops of this particular cup, so I will note it down, and I am trying to look for the water content where this particular soil mass gets closed after an application of around 25 number of blows. So this is one apparatus which is used for the determination of liquid limit. So if I have more water content, then it will be after say 10 number of blows also it can get closed up. If it has less number of less amount of water, then you may have to require to say give 50 number of blows, then also it is not closing down. Normally I will prefer to go when it closes down in the ranges from 15 blows to around 35 number of blows. So what I can do, I can initially add some water content, see if it is closing down at 15 number of blows, I will add some more water. Then I will again see how many number of, I cut down the this groove and again C for it. So this is how it is repeated, and finally you normally look for the one where it gets closed down for around 25 number of blows. So this plot is plotted between these drops and your water content. On the other hand, when the plastic limit is determined, as I said, this is the water content. If you reduce water content below this particular one, the soil may start crumbling down or it reaches to a semi-solid. So I'll take a soil mass, I'll add a moisture content to it, and I'll try to rub it down into a thread. And this thread should be a typical of 3 mm diameter. Now if this is easily formed, then again what I'll do some kneading. So the end, then again I'll start it. So this will reduce the water content, I'll reduce it. And normally when you roll this over the surface, normally you go for around 80 to 90 strokes in 1 minute. One stroke is going one forward and coming back. So I'll keep on giving this stroke, and I want to see the water content where this thread starts crumbling down. So that particular, when it is around a diameter of this particular one 3 mm. So that is the water content where now it is getting cracks and it is converting to semi-solid state. So I need to know these two limits, the liquid limit and the plastic limit. These two limits gives me an idea how much is the range. One is where it is acting as a fluid because it starts flowing, and the second is when it is behaving as a semi-solid. So in between that range it is holding the water. So that gives me, I want to get an estimate of that one, and that is known as the plasticity index, which is my liquid limit minus plastic limit. So this gives, plasticity index gives you idea about the plastic nature of the soil. And if a sandy soil is there, then definitely when you are going to look for it, you will not be able to form a thread of it. So if a sandy soil is there, we will say that it is a non-plastic because you are not able to find it. And there may be certain soils you may have very little difference between the liquid limit and plastics limit, so you can, even it can be 0. So the value can be also reported as 0 when there is the plastics limit is equal to your liquid limit. So the water holding capacity can be estimated, or the plastic nature of the soil can be estimated through this plasticity index. Now another important thing is free swell index, which gives an idea how much the soil can swell in the presence of water. So for this, because this swelling will depend upon different other factors, it will depend upon your gradation, it will depend upon, see, actual magnitude of swelling pressures developed, and if there is a swelling soil, you have put some layer over it. When water comes into its contact, it swells. Now it swells, it pushes your pavement structure up in upward direction. So this is not good for your structure life or for the performance. You want to have soils which have low swelling potential. So I need to determine the swelling index, or I'll call it as free swell index of the soil. So this free soil index is a measure of the increase in the volume of soil when it is submerged in water without any external constraints. I am not going to put any external constraints here in this case, and this gives an idea how much it can damage, especially because of the swelling which can happen, especially in expensive, when finer clays are there, or the clays which have a higher plasticity index, they have a higher swelling potential. So this can be estimated through your free swell index. This will depend upon other parameters also, water content, surcharge loading, several other environmental factors, but this is a simple test to get an idea how much is this swelling potential of a soil. So one, I can do it, I can put my soil sample, again the one which is passing 425 micron, one I'll put it in these graduating cylinders, one will be having kerosene in it. Why kerosene? Because it is a non-polar one, there will be no expansion or swelling of soil will happen. Second is the water, second I'll put it inside the water. So there the swelling, free swelling of the soil will take place. Now there two volumes, I'll leave it, this sample of the soil in these two cylinders having kerosene and water for a period of 24 hours, a standard weight of around 10 gram as per the codal provisions requirement is put. Then I will see what is the volume, VD and VK I will measure. VD says volume of soil specimen read from a graduated cylinder. These are graduated cylinders. Here you can see the graduated marks are there on these cylinder. So, I will get the volume containing distilled water and kerosene. So, this is the volume of soil having distilled water, this is the volume in case of kerosene. So, I am just going to see how much expansion of volume has taken place. So, this gives me my free swell index, and it says that expensive clay with free swelling index higher than 15% should not be used as fill material. If you have to raise your road level, then it should not be used as a fill material because of this high swelling potential. Even certain soils may be there which have a swell index less than that one, then also it says that they can be used as fill material, but you have to ensure if the subgrade and the top 50 centimeter of your embankment just below the subgrade are non-expansive in nature. Always you will prefer to use a material which is non-expansive in nature when you are doing the subgrade construction, and you will try to keep it at least 50 centimeter below the subgrade also, the embankment part, with a non-expansive material. Now, the MORTH also recommends that there is a requirement, if you are using any subgrade material, the liquid limit should be preferably less than 50%, the plastic limit should be less than 25%, because, and we will always prefer that this, especially the reason which will come up is in terms of plasticity index. We will try to have a soil with a lower plasticity index value. So, this is we indirectly try to restrict use of soils having a higher plasticity index, and these are the requirements which we will discuss again when we will come to the granular courses. These are for base courses requirement, these are granular sub base courses requirement. Here the requirement, it says that the liquid limit shall be less than 50% and the plastics limit should be less than 25%. So, expensive clays exhibiting marked swell shrinkage properties when tested as per shall not be, this we already discussed that they should not be used if the free swell index is more than. So, these are some traditional, specifically in terms of the Atterberg limits and in terms of the gradation requirements. In next lecture, we will discuss more about the optimum moisture content, maximum dry density and California bearing ratio. Thank you.